Good afternoon. Welcome to week 4 of the NPTEL course on coherence and quantum entanglement. Sorry. So, we are into week 4 now. 1 month of the course is completed and 2 more months are there to go. So, roughly 1/3 of the course we have completed now. So, let us begin with the problem set for week 4, wherein we have seen the Van-Sittert-Zernike theorem and how the cross-spectral density function is represented using that Van-Sittert-Zernike theorem. And there will be 3 problems in this problem solving session that I will be discussing. So let me read out the first problem. Problem 1. For a spatially incoherent source, the propagation equation within the far field approximation takes the following form known as the Van-Sittert-Zernike theorem. It is given as follows. So, this is for the propagation of the cross-spectral density function, where r prime is the source coordinate, s is the spectral density of the source, and then based on this Van-Sittert-Zernike theorem, we are supposed to solve these 3 parts to this question. Part A. Find the exact expression in the far field for the cross-spectral density function if the source is spatially incoherent, has constant spectral density, and is in the form of a square-shaped aperture of side A. Part B. Since we started with the spatially incoherent source, the coherence area at the source is of course 0. Make a reasonable estimate of the coherence area in the far field at Z. Is the area finite? Comment on what caused the field to acquire a finite coherence area upon propagation. Part C. Consider the spatially incoherent source to be in the form as shown in the figure. The source is kept at 0 and assume that the spectral density is a constant, and then derive the expression for the cross-spectral density W at a given value of Z. So the shape of the source is given as follows. It is basically 2 square-shaped apertures separated by a distance 2D. Center to center distance is 2D. Then this source is kept at Z equal to 0. And the source, let me clarify, the source is at Z equal to 0. And then the field propagates, and then we are looking at a finite value of Z. So, kindly read the question once again for a few minutes. See the expressions for the cross-spectral density and the spectral density, and try to understand what exactly the question is about. Try to recollect what Van-Sittert-Zernike theorem is. The expression is given over here. And just try to read the question once again and write down the first few steps that would be required to solve this problem, and then I will discuss the solution. So I hope now that you have spent a few minutes trying to read the question and trying to understand exactly what we are supposed to do. So let me start solving the question part by part. So let us look at part A. Let me rewrite the Van Sittard-Zernike theorem. So here we are given that the spectral density is a constant, and this area A over which we are integrating is a square of side A, and let us write this uh, in Cartesian coordinates now. So in Cartesian coordinates, the cross spectral density will be given as follows. S naught comes out of the integral because it is constant. Now, under the far field approximation, S1, which is the following in terms of the coordinates, Cartesian coordinates. This under the far field approximation can be written as follows. We can replace R1 by Z. Similarly, we can write the Similar expression for S2, which is approximated as follows. Again, R2 is approximated as Z. This is coming from the far field approximation, which says R1 and R2 are approximately equal to Z. So now this S2 minus this exponent term, this term right here, this term we are writing over here in the far field approximation. And let me call this equation 1. So now, using this approximation, we can rewrite our cross spectral density function as follows. Notice that we are replacing R1 with Z only when it is only when we are looking at these terms x1 over R1 or x2 over R2. Why? Because the R coordinate is much larger than the x coordinate, and that's why we are replacing it with Z, which is also much larger. But inside this exponent I, k, R2 minus R1, both R1 and R2 can be comparable, so we cannot replace that with simply 0, because in the phase, small changes in the phase can cause significant changes in the result. Similarly, we are not substituting it down in the denominator because there's not really any need. We substituted it inside this integral because we wanted to simplify our integral. This is because the limits we have put, because for square aperture, which is centered at origin, the limits of integration will be from minus a by 2 to plus a by 2 for both x prime and y prime coordinates. Now we can separate the x prime and y prime integrals because they are separable. They are in the separable form. Now let us look at this integral of this exponential. So this integral, let us see what it reduces to finally. Because our given integral is also of similar form. So this comes because e to the power I theta is cos theta plus I sin theta. And this gives us the following. So sin theta by theta is sinc theta. And let me call this equation 2. So using this, we get the final expression for the cross spectral density. Let us put it all together. So this is the final expression for the cross spectral density function. Now we can move to part B to find the coherence area. So part A was finding the exact expression for the cross-spectral density function, which we found. And then part B is to make an estimate for the coherence area. So the first zero of the sinc function that will help us in finding out the area of coherence. This occurs when the argument, which is k x2 minus x1 a over 2z is equal to pi. That is when the first zero occurs, because sine pi is 0 and sine 0 by 0, the sinc 0 is actually equal to 1, because limit theta tending to 0 of sine theta over theta, that is 1. So this gives me x2 minus x1 equals 2 pi z over ka. Similarly, the first zero of sinc for the y coordinate this will occur again when the argument is pi. Thus we get the coherence area at z as the product of this and this coherence area is finite. And we can think of this in a cartoon expression, like in a cartoon representation. So let's say let us say that I have a source which is incoherent and it will spatially incoherent, so the k vectors will be all over. And if I am looking at a plane over here, then within this area, let us say I'm looking at this area within this area I have all these k vectors which are contributing. But now if I move further away, if I keep that same piece of area further away, now I see that within the paraxial approximation, only these k vectors are going to contribute. So now these k vectors are uh, more parallel to each other, more or less pointing in the same direction or similar direction. If we move further away, then we will see that even fewer k vectors will contribute, and those k vectors which are contributing will be more and more parallel to each other. So there will be less angle between them. So this is like a cartoon representation of why an incoherent field picks up a finite coherence area as we propagate further. So this is because we are in the paraxial approximation. So let me write down the statement. So we obtain a finite coherence area upon propagation, even if we are starting with a spatially incoherent source. When we are far away, so when we are far away and when we are looking in the paraxial approximation, this is when this effect appears. So the field contribution is from nearby points. So if we have a source, so if it's a square source, then from nearby points only we have the field contribution, not from points which are very far away in this source. And since they are from nearby points, they become nearly indistinguishable. As we move further away. So finite coherence area is obtained upon propagation even from a spatially incoherent source in the far field. This is because in the far field, when we are in the paraxial approximation, the field contribution is from nearby points which become indistinguishable as we move further away from the source. So this completes part B as well. Let us now move ahead to part C. For part C, let me copy this source. So let's see the origin. Let me keep it over here in the middle. So this is x prime axis. This is y prime axis. Now for this source, let us look at what the integration area A will be. So over both the squares we need to integrate. Now W can be then written, let me rewrite in the Cartesian coordinates. This is, I'm just rewriting the Vansittart-Zernike. So just read it in the Vansittart-Zernike. Now we are given that the spectral density function is a constant, and since we are in the far field and we are making use of paraxial approximations, we can make use of equation 1. So equation 1, from here we can make use to approximate this part. So this will be written as approximately this is coming from equation 1. So therefore we can write RW Again, the integrals are separable in x and y, and s naught comes out of the integral. And from the integration area A, we can write down the limits. So let us simplify it further. We can take one integral common in the summation. The following integral will be taken common. Now we can make use of equation 2, this integral of the exponential, to evaluate the integrals. So this first integral then becomes the following sinc function. And let us call this I1 and I2, these integrals. So this integral over here, I'm calling this I1, and this is my I2. So let us evaluate I1 first. So the limits are shifted, they are not centered about origin. So it will not be simply a sinc function, there will be a shift in it. Here I have made the substitution. Beta is k y2 minus y1 over z. I am just simplifying it. And now putting in the expression for beta. So this is the final result for I1. Similarly, we will get for I2 as well. So this is I1. Similarly, we will get for I2. Okay, so now this will be plus sign because here it is plus d, here it is minus d. Therefore, and this is I2, sinc term is common. Exponential, we have one minus term and then sum with a plus argument. One has a negative argument, one has a positive argument or exponent. So this gives us cosine function in the end. This is 2 times cosine beta d, where beta is once again so this is I1 plus I2. So then finally we can write W, the cross spectral density function. So that's the final expression for cross spectral density function. So take about a few minutes to just go through what we have done in problem 1 before we finally move ahead to problem 2. So we made use of the Van-Sittert-Zernike theorem to find out the expression for cross spectral density in the far field and estimate the coherence area, and also a different kind of source. For that also we found the cross spectral density function. Just go through it once again. Okay, so let us proceed to problem 2. There are 4 parts to this problem. Consider the field U of a Gaussian beam, and the expression for U is given, which is the Gaussian. Is this field spatially coherent? And what is the coherence area of such a field? Part B. What is the spectral amplitude for such a beam? Part C. Next, consider the propagation of the Gaussian beam. First of all, show that the diffraction integral reduces to the following expression within the paraxial approximation. So again, we are making use of the paraxial approximation. Sorry, there should be, oh, there's a typo. This should be z squared is greater than this, or else we take z is greater than square root of this. And within the paraxial approximation, we have the expression for the field at a given value of z. This is the diffraction integral. Then we have to evaluate this field at z for a Gaussian beam with the amplitude, and we need to reduce it into these following, reduce the expression by making use of the following quantities, which is the Rayleigh range zr and the beam waist omega naught, and the radius of curvature capital R. So then part D, is the beam at Z spatially coherent, and what is the coherence area of the beam? Again, take a few minutes to read the question again, to look at the diffraction integral and try to understand how we can proceed in this question. Okay, so let us now start solving. Let us look at part A. This is the field expression at z equal to 0, and it is Gaussian. Omega naught is the beam waist. For this, we need to write down the cross spectral density function. and here we have z equal to 0. We are looking at z equal to 0. Now we need to find the degree of coherence. So degree of coherence is W divided by the intensities. That's my degree of coherence. Let us plug in the expressions. And everything in this numerator and denominator in this expression cancels out, which gives us the degree of coherence as equal to 1. So degree of coherence 1, that means the field is completely coherent. And which further implies that the coherence area is infinite. Next part is to find the spectral amplitude. This is the this is how we find spectral amplitude from the field amplitude. It's a Fourier transform. It's Fourier relation, so we need to find out this Fourier transform. So the integrals are separable in x and y coordinates. This is the Gaussian integral, the value of the integral. So therefore we will get our spectral amplitude. We can make use of this result to evaluate the integrals. So this pi cancels out, and finally we are left with the expression for the spectral amplitude as follows. this completes part B. So in part C, we are supposed to evaluate the diffraction integral. Now we will make use of paraxial approximation. This is the paraxial approximation. So let us look at how we will represent R in Cartesian coordinates. Now, making use of the paraxial approximation, this will paraxial approximation and the binomial theorem. So putting this in the expression for the diffraction integral, we will get the following. So we will approximate R to be Z in the denominator over here in the far field. Sorry. Now for the Gaussian field, we'll put the expression for a Gaussian field amplitude. And the x and y coordinates are separable. Now again we'll make use of the Gaussian integral. Let us call this one over here equation 3. So making use of this Gaussian integral, we'll get the result. Now we will simplify it. So in terms of these expressions, I'm just using some algebraic manipulations and simplifying. So this 2 pi z cancels out. and this z cancels over here. So this term in the exponent we can simplify. Let me bring this down over here. And also we can write this Zi plus Zr as the amplitude times the argument exponential of the phase, and this amplitude this I'm just writing the amplitude again. So further, this exponential can be written by making use of this simplification that we have just done. This Z cancels. And also, if we combine this 2 with this amplitude part over here, and also this denominator. This will give me this 2 cancels, 1k also cancels out. So putting this all of this together will give me the final expression for the diffraction integral, which gives me the field at a given value of z, given that we know the value of the field at the at z equal to 0. So this completes part C. Part D is to find out the coherence, and the field is spatially perfectly coherent. So the coherence area is infinite. This comes, we can look at part A, how we have done. So repeating the same thing but for Z. So let me just revisit. So W is U star, this is W, then mu is W over I'm using P1 for short of the 0.1. Let me so when I say P1 is essentially x1 y1 z, and P2 is x2 y2 z. So this, when you do it, everything in the numerator and denominator cancels out, giving 1. And also, we saw that the field was spatially perfectly coherent to start with. At z equal to 0, mu was equal to 1. Mu was equal to 1. And we know from Van Sitter's Zernike, we saw in the previous problem, we saw over here in Van Sittert-Zernike theorem that if we start with spatially incoherent source, like zero coherence at the source, it tends to pick up finite coherence upon propagation. So when we propagate, the coherence area increases, or the coherence increases. So if we have perfectly coherent to start with, it will remain perfectly coherent even after propagation. So so from these two, you can directly say that the field will remain spatially perfectly coherent even after propagation. So this brings us to the end of problem 2. There were a lot of algebraic manipulations involved over here. So take about a few minutes to grasp all of this before we proceed to problem 3. Okay, someone is asking how from someone is having a question in party. How from mu equal to 1 we are claiming that the coherence area is infinite? Okay, so Mu is called the degree of coherence. It basically quantifies the coherence between any two given points in the field. Now, if we take any 2 points in the field, and if they are completely coherent amongst each other, then their degree of coherence is 1. That means you take the field, and if you consider any 2 points in that field, they will be coherent to each other. So that is what mu equals 1 means. And these 2 points can be as close to each other or as far away from each other, because mu, as you can see, is a constant. It is 1 and it is independent of the location of these points. As a result, we can take our points to be as far away from each other. Like the distance between these 2 points we can take as infinite. So that means if 2 points are infinitely far away, still the coherence between them is 1. So that means that the coherence area is also infinite, because our points can be kept at infinity in the source and still they will be perfectly coherent with each other. So that is why if mu is equal to 1, then the coherence area is infinite. So in this example, where we started with a completely incoherent source, we saw that the coherence area became finite after propagation. Okay, so problem 2 is complete. We can move to problem 3. This is on Young's double slit experiment, but we do not really have much time left for today, so maybe we will take this up in the next session. We will start with problem 3 in the next session, in the next problem solving session, before solving some new questions, because today the time is not there. Time is very short for us. We have only about 10 minutes. So what I can do is, maybe I will just read out the question for you so that you understand what is to be done, and you can also try and attempt this question before the next class. So problem 3, consider a spatially coherent constant amplitude plane wave field. The field is temporally stationary with the spectral density, which is given as a Gaussian expression, and omega naught is much greater than delta omega. So delta omega is very small. That means, so very small region of frequencies will contribute. Very small region of frequencies will have a significant value of the spectral density S omega. Now, suppose you are given a Young's double slit setup. The separation between the two slits is 2D and the distance to the screen is R, with R much larger than D. That means the screen to source distance is much greater than the slit separation. The size of the two slits are negligibly small. That means we can consider that the slit width is tending to 0. Describe how one could find the frequency bandwidth delta omega of the field by measuring the intensity Ix on the screen as a function of x. So our coordinates are drawn. Z coordinate basically is in the direction of propagation of the field, and on the screen the pattern that we are looking is along the x coordinate. So we have an incoming field over here. It falls on these two slits, which are infinitesimally small, and then it propagates, reaches the screen at z equal to r. So This is my screen. And once it reaches the screen, there will be some interference pattern, Young's double slit interference pattern that we will see. But this time, typically in your school days, in your class 12, what we study is a plane wave. So the field that is coming in is a monochromatic plane wave, single frequency. But here the plane wave field that we have is not single frequency. It has a range of frequencies defined by this spectral density S omega. The range of frequencies delta omega centered about omega naught, which will contribute. So it is not perfectly monochromatic. It is nearly monochromatic if, because delta omega is very small, so very small the like number of frequencies about omega naught will contribute, but it is not strictly monochromatic. So that's the difference between this question and what you would have studied in your school. So that's the question, and what we have to do is, by looking at the interference pattern, we have to make an estimate of the bandwidth delta omega, that is the range of frequencies which are actually contributing to this interference pattern. So that's the problem. Please read it once again, take a few minutes to understand. Sorry. So okay, so that's the question, and since we do not really have much time left, we will address this question in the next week, next Saturday at 3 p.m. So for those of you who have joined late, let me once again put the link to the YouTube channel for these problem solving sessions. So every Saturday we have these 2-hour problem solving sessions from 3 p.m. to 5 p.m. where we discuss problems like these, and typically we solve these theory questions and also see numerical simulations. For example, for this problem 3 also we will look at some numerical simulations in Mathematica, but this will be discussed in the next class. So in this week we looked at Van-Sittert-Zernike theorem and propagation, both propagation of the cross-spectral density function, which is given by the Van-Sittert-Zernike theorem, and also propagation of the field, which is given by the diffraction integral. So if we know the field at z equal to 0, then we can find the field at a given finite z by means of diffraction integral, which was what we did in problem 2 over here. And if we know the cross spectral density at z equal to 0, then we can find it at finite z by means of the Van Sittert-Zernike theorem. So Van Sittert-Zernike theorem actually is the far field approximation. So in the far field, like very large value of z. So these were the topics that we mainly focused on today. And the interesting thing that we saw is that even if we start with a spatially incoherent source, upon propagation it gains a finite coherence area. And this is a direct consequence of the Van Sittert-Zernike theorem. Sorry. Yeah, so this brings us to the end of today's lecture. If you have any questions, please feel free to unmute and ask or put it up in the chat box. So there are two integrals which are really important, and let me highlight them for you. So one is this integral which gives this sinc function. This is easily evaluated, and the other is the Gaussian integral. Where is it? Over here. So this you should actually memorize. This comes from the beta gamma functions. You can actually evaluate this, but you should memorize this. This is very important, this Gaussian integral. And we will be making use of this Gaussian integral at a lot of places in physics, not just in this course but elsewhere as well. So you should be, like memorize this Gaussian integral, the result. Okay, so that's all for today. Thank you very much. You may now leave the meeting.